Of course, we have the midterm coming up Thursday. So what we're going to do today is review for the midterm for however long that takes. And if that takes the whole period, it'll take the whole period. Otherwise, we've got other stuff we can talk about. So here's the details for the midterm. It's on Thursday, March 1st, here at the usual time. You can bring a sheet of notes. Otherwise, it's closed book. And Stefan is going to be doing reviews today, one at 3 o'clock and one at 5 o'clock. It's next door in Web L102. Okay. I've also in the class schedule, if you look in the class schedule on Canvas, I put a couple of documents called PS3 key ideas and PS4 key ideas and so forth. So it's not exactly solutions to the assignments, but it's explanations of the solutions to the problems that aren't, multiple choice or, automatically graded. Okay? So you can take a look at that. Before we start, are there any questions or problems about it at all? Yeah?
So, we'll just ask a question from last week. Will the reviews at 3 and 5 o'clock be recorded?
Stefan, will the reviews at 3 and 5 o'clock be recorded?
If I get someone to record them, I'll talk to one of the TAs.
Did you have somebody there record it for you, or did it have to be like a training? Like, did you set it up and then just point the camera? Just trying to problem solve.
I'll talk to the TA.
All right, so maybe. Any other questions? Yeah?
Is there any reason to come to both reviews? Will they be pretty similar? Just writing stuff.
They'll be similar. I mean, it just depends on where the discussions lead people. But yeah, basically, he's going over the sample midterm I posted. So if you look in the schedule, you'll find the sample midterm last year's midterm. Any other questions? Yeah.
Do you have any other previous midterms that you can give us?
I'm just going to stick with the one. Anything else? Yes?
Will this midterm be as long as practice ones?
No, this midterm will not be as long. Last midterm was too long, as it turns out.
Oh, thank you.
There's a downside to that. That means the questions will be worth more. And so a single mistake can cost you more points than on last year's midterm. That's just, yeah.
Will we have an opportunity today to ask questions from last year's midterm?
Sure, you can ask anything you want. Okay. So if you have a particular question in mind, maybe ask it when we get to the right point in this review. Any other questions? Stefan, you got it rolling? Okay. All right, so this will be a short review unless you ask more questions. So essentially, I'll go over topics we've talked about, but you'll need to ask questions or I'll just plow right through. All right, so what we'll cover is the first weeks of lecture, the first 6 weeks of lecture, plus there was this graphs in the wild thing that we talked about at the beginning of week 7, which is related to the first 6 weeks. Chapters 0 through 4 in the book, although chapter 1 just barely, just modular arithmetic, similar to what was on PS6. These review slides, and PS1 through PS6. As I mentioned, for PS3 through PS6, there are some notes on problems that weren't auto-graded. Okay, these are the major topics we talked about, so I'll have a slide or so on each of these topics. We began by talking about complexity analysis and basic algorithms and data structures. That was sort of the first week and a half or 2 weeks. We talked for a while about divide and conquer algorithms. That was chapter 2. We talked about graph decomposition, which amounts to depth first search. That's chapter 3. We talked about graph search, which amounts to breadth first search and shortest paths algorithms. That's chapter 3, I think I said. And then, or I guess chapter 4. And then modular arithmetic, which was the very beginning of chapter 1. So that's what we've been doing. Okay, so here's a good place to start asking questions if you have any. This is what you need to know about complexity analysis. The whole idea behind asymptotic analysis. Why do we do asymptotic analysis? Let me pause there and see if we can answer the question. Why do we, there are lots of other ways we could do analysis. We could do experimental analyses. We just time how long things take. We could dispense with asymptotic analysis and just come up with something more precise. So why do we do asymptotic analysis? It's sort of our go-to technique. Yeah?
Well, I think it forces you to understand the algorithm better than just like running it and seeing the numbers.
Okay, so doing an asymptotic analysis versus running it, yeah, anyone could time an algorithm without really understanding how it works. So I think that's true. Asymptotic analysis makes you think about the algorithm. Yeah?
Gives you a way to compare algorithms and see efficiency.
Okay, it gives you a way to compare algorithms, at least how they would behave in the limit. Yeah?
I think it kind of runs hand in hand on testing edge cases. I know it's not exactly testing analysis, but it's a similar concept where what's the worst that could happen? Let's look at the very edge worst cases of things.
Okay, well, worst case asymptotic analysis would look at the worst case. Asymptotic doesn't mean worst case. Asymptotic means as the problem size is what happens to the best case, the average case, the worst case. Yeah?
It's general and can be applied to a different amount of solutions if you use the algorithm for. So every time you use something like Dijkstra's, it's not going to be the same problem. But when it's asymptotic, it's going to perform based on how fast the CPU runs or what the actual problem is.
Okay, so it's predictive in a way. It's not going to tell you the exact running time for any problem size, but it's going to tell you the trend. Yeah?
It lets you bound runtime for large N.
Okay, he said it lets you bound runtime for large N. Yeah?
It's not bound to a machine that you're running.
Okay, so now we're getting at why don't we, do something else. It's not specific to a type of machine. It's an explicit timing would just give you a prediction for a particular kind of computer. But why don't we get something more precise? I mean, basically, when we do asymptotic analysis, we just look at the high order term, and even then we throw away the constant. Yeah?
I guess computers keep getting bigger, and I think problems keep getting bigger, so the only thing that's really relevant for the future is know where the timing is headed.
Okay. All right. Yeah?
I was going to say, it's the only thing that matters to see how our algorithms grow with scale.
Well, he said it's the only thing that matters. I wouldn't say that's the only thing that matters. I mean, if you had an algorithm that took 4 n squared seconds, and I told you I had an algorithm that took 2 n squared seconds, would you prefer mine? It's twice as fast. Leading constants are important. I think your book has a line in it, something like, people would stay up all night to get a factor of 2 improvement. I bet some of you have done caddis problems where you wish you could have gotten a factor of 2 improvement. So why do we ignore the leading terms? Yeah?
I think it lets us classify algorithms into certain groups that we can reason about one group versus another.
Well, certainly, yeah. If we ignore the leading terms, there are more we just call algorithms n squared. And yeah?
So I think it lets you plan your algorithm before you actually write any code. And that way you kind of have an idea of how to run.
Well, yeah, it's true that we do asymptotic analysis. You can do it without referring to a particular implementation. But wouldn't it be better if we could say this is a 3n squared plus 5n minus 2 algorithm? Why don't we do that? Yeah.
If you're looking at the problem as n goes to infinity, then you can throw out the lower order terms because those become insignificant compared to the highest order. So as the problem is getting bigger, we only care about like the doubling behavior, for example, in general.
Okay. So as the problem gets bigger, the lower order terms become irrelevant if what you're looking at is the doubling behavior. I mean, the bottom line is, if we could do the analysis and pin down the leading constant in low order terms, we would. It's just too hard. It depends on too many things. It depends on the language it's going to be implemented in. It depends on the type of computer it's going to be run on. So just sort of out of necessity, it's not like there's a higher purpose to it. Out of necessity, we ignore those things because otherwise it's just too difficult to pin down the algorithm. Yeah.
Isn't it partially because we also don't know, like, once it goes into like assembly code, we don't know how long certain steps are going to take.
Right. So he's saying, it gets translated to assembly code before it runs. So yeah, and that's that's just saying the runtime depends on the compiler, depends on the operating system, depends on the computer. So all those details, the low order terms, the leading constant, depends on that stuff, and it's just tough to. It's hard. You can't really generally account for them all. So we're just sort of left with. We do it asymptotic analysis because that's the best we can do too. Now, when I say doubling behavior, what do I mean? What do I mean by doubling behavior in an algorithm? Yeah.
So how the timing changes as you're doubling n, whatever.
Okay. So what happens to the running time when the problem size doubles? And all these common complexity classes that we've looked at, there's a characteristic. So what happens to the running time when the problem size doubles for an O of n algorithm? Let's say a theta of n algorithm. It doubles. Okay. What about if it's theta of log n? What happens to the running time when the problem size doubles?
Increases by a constant.
Goes up by a constant. If it's n squared, quadruples. Okay. What about n log n?
Doubles just a little bit.
Yeah, doubles. It's a little bit worse than doubling. Okay. So it's good to be familiar with that stuff, and to know how to derive it for a different measure. I mean, like, what about n cubed? How can you show that if it's n cubed, it goes up by a factor of 8? What's that? Yeah, you compute the ratio between 2n cubed and n cubed. In the numerator, you put the double size problem cubed. In the denominator, you put the single size problem cubed. So it's just 2n cubed over n cubed, and that ratio is 8. So it's easy to derive new ones. We talked about experimental complexity analysis and how to do it. We talked about summations to analyze loops. Okay. And there's a problem on the sample exam that someone was asking me about before class. So why don't we do that one here? So the loop was something like this. Okay, so this wasn't exactly a complexity analysis. We're trying to come up with a formula for what the value of total is after the loop runs. But it's the same kind of stuff you do in a complexity analysis. The total starts at a 0. So how do you approach a problem like this? This is the thing I forgot, is n is equal to 3k. So I want the complexity in terms of k. Yeah?
Multiply 3
Multiply 3 times n? No, you're right.
N over
No.
3 times n.
So you're multiplying n over 3 times n?
Yeah.
So that gives you n squared over 3?
So,
I think that sounds a little too easy to be right. Maybe it is. Yeah.
So you see that total plus plus is going to get 3k times the first run through, and then it's going to
Okay.
be 3k minus 3, then the second time, then 3k minus 6, and then
All right. So.
it's just
All right, that's good. So the way I approach it is I think, okay, the first time through the loop, I will be 0, right? Right. What will get added to total by the inner loop?
N.
Okay, so that inner loop will run n times, right? It'll be j equals 0 up to n minus 1. So it'll add n things to the total. So I say first time through the loop, actually,
3k, right?
it adds, I want to say it adds 3k. So that's what n is. Okay? All right, someone else tell me the second time through the loop, I will be 3, right? What will get added to total? 3k minus 3. Right? Next time, it'll be 6. 3k minus 6. And what will be the value the last time through the loop?
0. Well, the second to last here is 3.
And what will be the value of I the last time through the loop?
3k.
Now, it won't be 3k. It'll be 3k minus 3. When it's 3k, the loop terminates. And what's going to be added that time? 3. Okay? Or another way to put that is 3k minus 1 times 3. Just to keep the pattern alive. Okay? So then it's just a matter of doing the summation. You got to add all those things up. Okay? So it looks like it's 3k times something. Well, times what? No,
Well, wouldn't it be easier if we just
scratch that. Okay, how do I do the summation? Okay?
So it's 3 plus 6 plus 9 plus dot 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 to 3k. So in that case, you can factor out the 3, so it's 3 times.
I'm not trying to add up the i's here. I'm trying to add up over here.
Yeah, that is, so it's, because the very last term is, remember, is 3, so 3 plus 6 plus 9 dot dot dot.
Okay, so he's turning it around.
Yeah, I'm going up rather than going down.
Okay.
And then you'll see that you factor out the 3.
So maybe my simplification wasn't a simplification. Let's say that runs 3 times. So adding up in this direction, he gets 3 plus 6 plus 9 all the way up to 3k. Now that's a better way to look at it. So we got to do that summation. Now he wants to factor out the 3's. 1 plus 2 plus all the way up to k. And that's equal to 3 times k times k plus 1 over 2. All right, so the first step was to, just figure out that, what this looking at that inner loop. For each value of I, what's the inner loop do? Then you get a summation and play with it so you can add it up. Yeah?
So, I'm sorry, why don't you care about I?
Why do I care about I?
Why don't you? Put an X over I and then check.
Well, I care about I, but what I'm doing is I'm trying to figure out what's added to total. Right? The question is what's total after the loop runs. So, I and j together determine that, but when I just break it down, and when I is 0, the first time through the outer loop, the inner loop will add 3k to total. So just for each different value of I figure out what's being added to the total. Yeah?
What's that confuses how you was 3k, 3k minus 3, that series to 3, 6, 9,
Well, I went back up.
previous term would be 3k minus.
Well, but if you notice, it's going down by 3 each time, right?
Right.
So the one before 3 had to be 6.
Okay.
The one before 6 had to be 9, and so on. So when you go up, you go from 3 to 3k by 3s. You don't see that? Do you agree that when we go from here to here, we've gone down by 3? We go from here to here, we've gone down by 3. So every time we go down a line, we're going down by 3.
Okay.
So if we got here by going down by 3, what was the one right there?
Up by 3.
It must have been 6. The one before that must have been 9. Before that was 12.
Okay.
All right? So you end up with 3 up to 3k by 3s. So that's how I got this and that. And that's a sum we can deal with. All right? Any other questions? Yeah?
Any rules about how we have to write out our algebraic expression? Is it 3 halves k times k plus 1?
Okay. The reason I ever proposed a rule on how you write out expressions is in a vain attempt to get Canvas to grade things automatically. And it never succeeds, and we end up doing it by hand. But the price I have paid for putting on the first assignment, trying to tell you exactly how to write, is every week Anthony asks the same question. How do we write out the answer? Okay? The answer is make it as simple as you can, and we're not ruled by the other grader. We try to go back and get things correct. You know, make sure correct answers get full credit. Okay? All right. Back to this. So that's an example of using a summation to analyze a loop. So in that case, if we're interested in the running time of that algorithm as a function of k, what would be the big O bound you could put on that loop we just looked at? If k was a parameter to a method that did what we just saw.
K squared.
K squared. It's O of k squared. Because we did the analysis and we got k squared. Yeah?
How about summing geometric series?
Yeah. Where do we see summing geometric series?
PS3-ish.
It was sort of an alternative using recurrence relations to analyze recursion. There's one geometric series that I want you to have memorized, and that's the sum of the first k powers of 2. Okay? So what is the sum of 1 plus 2 plus 4 plus 8 all the way up to 2k? 2 to the k. 1 less than the next power of 2. So it would be 2 to the k plus 1 minus 1. So sometimes often that's a useful thing to know. Beyond that, there won't be anything on the final that requires summing any other geometric series.
Midterm.
On the midterm.
You actually go back for 1 second to
Yep.
the summation. I have one more question.
On the example I did?
Yeah.
Okay.
So look, use the end. I ended up with just 3 for the last term.
Well, when I is 3k minus 3, think about that loop. J is going to start out at 3k minus 3, and it's going to stop when it hits n. So it'll go 3k minus 3, 3k minus 2, 3k minus 1, loop ends. So the inner loop will iterate 3 times. Right? So from the point of view of the inner loop, this is the starting value, and it ends at 3k. 3k minus 3 is 3. Yeah?
Could you flip it so that I is the...
Okay. Yeah.
Did you write our geometric series?
What, geometric series?
Yeah, the one you wanted us to remember.
Okay.
2, 4. Minus 1 at the end.
Yeah. You know, I learned this, I was something like 10 years old, and my father had an adding machine. We didn't have calculators when I was 10 years old. And I was, for some reason, I wanted to calculate powers of 2. And I figured out that, okay, let's say I knew 4 was a power of 2. Well, what I discovered was I would do 1, I would add 2. No, it wasn't a mechanical one, it was actually an electric one. I got 3, and I realized, oh, the next one's 4. I would say plus 4, and I realized the next one was 7, and 1 more than that is 8. And so I was able to generate powers of 2 as long as I wanted. So that's why it's near to my heart, because I did that at an early age. So it's hard for me to forget. Okay. Any other questions before I make this disappear? Okay. We learned to use recurrence relations to analyze recursion. And I'll have more to say about that in the subsequent slides. And then we have these notations here. So when you say something is O of f of n, what are you saying? It's an upper bound. It's not just, it's an upper bound on whatever f of n is. It doesn't have to be runtime. It could be runtime. It could be memory consumption. It could be best case runtime. It could be worst case memory consumption, and so on. But it provides an upper bound on whatever you put it, wherever you're saying. An upper bound on the asymptotic rate of growth. An upper bound on the doubling behavior, if you will. It's not an absolute. You know, 4n squared is O of n squared. It's not true that n squared is an upper bound on 4n squared. Asymptotically, though, in the limit, they grow at the same rate, and that's what the upper bound is on. Asymptotic rate of growth. What's omega? That's a lower bound on the asymptotic rate of growth. Theta is just a way of saying the upper bound and the lower bound are the same. And then what about these two outliers here, little o, little omega? Yeah, that's still an upper bound and that's still a lower bound. But in this case, they have to be loose. So if this thing is like greater than or equal, this would be greater than, but not equal. Okay, so n squared is little o of n cubed. It's not little o of n squared. Same conversely for little omega. Okay. Okay, we talked, basically we reviewed basic algorithms. So we talked about linear search and binary search. So, I mean, that's just something that you should just automatically know. Linear search takes linear time, binary search takes logarithmic time. We reviewed selection sort, insertion sort, quick sort, and merge sort. And their various, these are n squared algorithms. I always like to say, find something nice to say about any algorithm. So what's something nice you can say about selection sort? It's simple. What about the running time? What? That's n squared in all cases.
It's good on small n.
Yeah, it works. It's nice. It works. Both these n squared algorithms work nicely on small arrays. What does it do less of than any other algorithm? It always does exactly the same number of comparisons. Yeah?
Fewer swaps.
Right. It only does, it does the minimum number of swaps. It does n minus 1 swaps. So I have on the past put on a test what algorithm would be best to sort elephants. The idea being that you can study the problem all you want and make lots of comparisons, but when it's nice that you only have to move the elephants the minimum number of times. Think about the difference between that and trying to sort elephants with quicksort. Yeah.
Well, in theory, you could take the weight of each element, sort the weights, and then actually move them at the end.
Yes. Yep, you could do that. You could come up with even fewer swaps if you analyze it that way. But anyway, selection sort does the fewest. It does a linear number of moves. What about insertion sort? What's nice about insertion sort? Yeah?
Can exit early after running through the list once.
You said it can exit early after running through the list once, which is another way of saying what?
As a best case of.
Best case of linear time.
It's a best case of linear time, but when does that best case occur?
When it's already sorted.
When it's already sorted, or and if it's fast even if it's just almost already sorted. Yeah.
Would you say, oh, okay, you just said that it has good performance on partially sorted arrays, which is what you said.
Right. So the running time of insertion sort is proportional to the number of, I think the word is inversions, but basically, insertion sorts by exchanging adjacent elements. So the running time is proportional to the number of adjacent elements you have to exchange in order to get the array sorted. So if it's close to sorted, it'll be fast. What about quicksort? What's nice to say about quicksort? Yeah?
It's n log n, the average case, and constant space complexity.
Well, it's not constant space, because you got to use stack space. Yeah, but it's n log n on average. The bad thing is n squared in the worst case. But there's something even better about quicksort than it's n log n. There are lots of algorithms that are n log n on average. Yeah?
It's in place.
It's what?
In place.
Still.
In place.
Yeah, it's in place, but yeah, as compared to Mertzsort. Yeah?
As a small leading constant.
Yeah, right. He said it has a small leading constant. It's quick. It's faster than Mertzsort on average. Forget about asymptotic analysis. It's faster than Mertzsort or heap sort on average. And then Mertzsort, the good thing about it is n log n in the worst case. But it's about half the speed of quicksort on average. Yeah?
It's also
Twice the speed, I should say.
stable. It's a stable sort. Isn't it?
Mertzsort?
Worst case is n log n.
Yeah. Mertzsort is stable. Quicksort is not. Yeah.
The other thing is merge sorted is easier to parallelize.
Yes, Mertzsort's very easy to parallelize. Because if you split the array in half, you can imagine sorting one half on this core and one half on that core, and then doing the merge. So, yep, it's easy to scale it up to however many processors you have there. Yep.
This is twice the memory though, since you have to have a whole copy of the array.
Right, it does take linear extra memory, because you can't merge in place. Unlike quicksort, you quicksort in place.
So how do we say that type of memory usage? Like quicksort uses n amount of memory, and Mertzsort uses.
Well, when you're talking about sorting, you talk about sort of extra space required beyond the array itself. So Mertzsort requires theta of n extra space. Quicksort, if you write it using tail recursion optimization, it takes log n extra space for the stack frames.
Do we count the Mertzsort's stack frame as well?
Well, yeah, Mertzsort uses stack frames, but it's log n stack frames, but that's less than, that's theta log n. But the extra array alone is theta of n, so the theta of n drowns out.
N plus log n.
Well, it's n plus log n, but log n is low order term. You can write Mertzsort also non-recursively, write it iteratively. Just take your array, do a bunch of 1-by-1 merges, and then do a bunch of 2-by-2 merges. So going from the bottom up, you can write it non-recursively. Okay, we talked about basic data structures like lists. So you should be familiar with how dynamic arrays work. This idea that when it fills up, you double it, or it doesn't have to double, but it goes up by some fixed percentage. Linked lists, the trade-offs between them. Linked lists are good if you've got your finger on a spot for doing assertions at that spot, or deletions, whereas dynamic arrays are good for random access, but not so good for inserting into the middle. We talked about two different ways of representing sets, binary search trees, or balanced binary search trees, and hash tables. And the same goes for maps. This is just 2420 stuff. Any questions about those basic data structures there? Yeah?
Yeah, sorry. What's the difference between a set and a map?
Okay, who can tell us what's the difference between a set and a map? Yeah?
With the map, it's the keys that you don't have to look at entry does, or the map is key value pair that you insert.
Okay, so with maps, you've got key value pairs. So, and then with a set, you just got keys. Okay? So they both use the same technology. It's just a matter of whether there's extra information riding along with the key. Any other questions? All right, and then we talked about divide and conquer. Now these are some examples of algorithms we talked about. Recursive multiplication, which turned out to be an n-squared algorithm. Caret-Seuvel multiplication, which actually improved on grade school and recursive multiplication. Quick-sort and Mertzsort are both examples of divide and conquer algorithms. Quick select, divide and conquer algorithm. The majority element algorithm we talked about and that you used on the CADS problem. Also a divide and conquer algorithm. So what's the characteristic of a divide and conquer algorithm? Is any recursive algorithm divide and conquer?
As you recurse, you break the problem down into smaller pieces.
Well, okay, so she said as you, each time, at each level, you make some number of recursive calls that breaks the problem into pieces. But you got to say more than, there's more to it than just breaking the problem into smaller pieces. Yeah?
Each piece is a sub-problem of the original problem, which means it can be solved in the same way.
Well, it's a sub-problem, yes, but there's still, to call it divide and conquer. Yeah?
Would you resolve the answer and then bring it back up and combine it?
Well, I mean, that's true. You know, making the recursive calls and then combining, that's true of all recursive algorithms, but we don't call all recursive algorithms divide and conquer. Yeah?
If you reduce the problem until it becomes trivial.
Well, but that's reducing to the base case, that's, any recursive algorithm does that as well. Yeah?
You have to know how many times the operation was performed and how much n was reduced.
Okay, so it makes a fixed number of recursive calls. Okay, imagine if you had an algorithm that took an array of length n and it made n recursive calls, for, you know, in some way. Okay, where the number of recursive calls depends on the size of the problem. We wouldn't call that divide and conquer. Think of divide and conquer as something we can analyze with the master theorem. So you have a fixed number of recursive calls being made, but there's more you got to say. Yeah.
So doesn't that mean that it'll make into a very specific time complexity, or the log terms that we talked about? Because we're dividing.
Well, so he's saying, well, let me just skip over that. I'm not sure what to say about it. Yes?
So speaking of the master theorem, maybe we should have brought this up earlier, but can you go over how you calculate A, B, and D?
Yeah, I'll go over that, but I'm still trying to pin down what divide and conquer is. Yes?
Are you trying to get at that the pieces need to be proportional to the length size?
Right. There's some constant by which you're dividing the size of the problem. So a common one is half. We divide the problem in half and make recursive calls with the halves. Or divide it into thirds, or divide it into two-thirds. But there's a constant that shows up in the master theorem. Okay? So an example where you would not have, couldn't apply the master theorem would be you have an array of length n, and you make one recursive call on an array of length n minus 1. Okay? So you're making a fixed number of recursions, but the size of the recursion is not, some constant times the size of the original array. It's minus 1. It's not times some constant. Yeah?
What if, let's say what you're breaking it up into is like exponentials, and it's like each time it goes through, it increases how many times it breaks it up.
Okay, so if the number of recursive calls goes up each time, then it has to be a fixed number of calls, and each call needs to be a constant times the size of the original problem to call it divide and conquer. Yeah?
Could you give us an example of an algorithm, a recursive algorithm that is not divide and conquer?
Okay. Let me save this. Okay, so some of those numerical algorithms, the integer algorithms that we're talking about. Okay? So he just mentioned GCD. So you compute the GCD of A and B. If we're not in the base case, what was it? The GCD of B in A mod B, right? So, I get that right? Okay. It'd be hard to apply the master theorem here, because what can you say? You're only making one recursive call, but you can't say that the size of the problem has gone down by some, it's gone down by half or a third or a fifth, yeah?
You also say that depth first search isn't
yeah. Think about depth first search. You can't really characterize the size of the subproblem in terms of the size of the original. Or think about quicksort in the worst case. Okay? So when you, in the worst case, let's say you're sorting an array of size n. Well, let's do the best case first. In the best case, how many recursive calls? Oh, it makes 2 recursive calls, but how big are the 2 arrays? Right? They're each n over 2. So you could analyze the best case with the master theorem. That's divide and conquer. But what's the worst case? The worst case, you get n minus 1 and 0. So there's no multiplicative constant that tells you how big the array is. It's just 1 less than it was originally. So those are some examples of what I wouldn't call divide and conquer. It needs to be a divide part.
Or evenly divide.
Yeah. Divide by a constant. The size is divided by a constant. Yeah.
Divide by a fixed constant.
Yeah. Divide by a fixed constant.
And with the second example, worst case, you don't know.
Right. You're not. The problem size is not being reduced by a fixed constant. Okay. So then we have the question over there, which was how do you determine A, B, C, and D?
C?
Forget C. How do you determine A, B, and D? Okay. Good question. So how do you do that? So let's make, we got A, B, and C. Let's just say it in words. What is A?
B.
A, B, and D. Okay. What is A?
A is the number of recursive calls.
Okay, it's the number of recursive calls. Okay, it's nice to say that, but then you're still left thinking, okay, you start with some big problem. Are we talking about the number, if you got to draw the entire recursion tree and count?
One frame.
Yeah?
Yes, the number of recursive calls, like, the first time you do the code is, or just when the code is set up.
Okay, so number of recursive calls, they get executed per call, other than the base case. And so you determine that by looking at the code, right? You determine A by looking at the code, not looking at the recursion tree. So if you've got a method here, and there's a recursive case, and in the recursive case you call F once, you call F again, A is 2. You made 2 recursive calls in the code. Now it's slightly more involved than just counting the number of recursive calls in the code. Why is it slightly more involved than that? Yeah?
Well, you could have, code that has if-else statements and only ever does 1 recursive call, or maybe it has like 3 of them in different if cases.
Right. You could have the recursive case look like this, and you say if something is true, make a recursive call, else make a different recursive call. So in that case, you wouldn't say A is 2. It never makes 2 recursive calls at that level. It only makes 1. So you would use an A of 1 in that case. Yeah?
Or the recursive call could be in the loop, and then we have to count how many times it goes through the loop.
Yeah, the recursive call could be in a loop. So you only physically see 1 call, but say the loop iterates 5 times. In that case, A is 5. There's 5 recursive calls are made. Yeah?
If the else didn't have a recursive call, would you still say it's 1?
No, if else doesn't have a recursive call, then it's a base case. So yeah, you got to look at when a recursive call is made, how many recursive calls are made, just from the method, not for all time. Okay, does that make sense for A? Okay, what about B? Yeah?
The branching factor.
Okay, branching factor. Well, that's nice since it's B. Branching factor. What do you mean by branching factor?
the number of ways you're going to divide the set at each level.
Yeah, in fact, I think branching factor is more like something for A. A branching factor is a number of ways it branches at each level of the recursion. So that's A, yeah?
The factor by which the output is reduced.
Okay. So, factor by which problem size is divided, let's say. Okay? So if the problem is being, if there are some recursive calls and each one is half the size of the original, A is 2. Problem size is being divided by 2 in each of the calls. Or it can be divided by 3, or it can be divided by 3 halves, or whatever. So it's a constant factor by which the problem size is divided. Now you may not see a division in the problem. I mean, what if what you saw was this? Suppose you saw, you got an array A as input, and in your recursive call, you just looked at the first, let's say n is the length of the array. Okay? So you made a recursive call using the first fifth of the elements in the original array. What would B be? 5. You're dividing the size by 5. Okay? Then what's D? Yeah?
Quick question.
Yep.
On one of the quizzes, we had an example where you look at like the first element in the array. I think there were 3 recursive calls. You look at the first element in the array, and then the first 2/3 sections, and then the last 2/3 sections, and then the first 2/3 sections again. And that B value ended up being 3 halves. Can you kind of go through that?
Okay. So he's asking about that weird sorting algorithm, sometimes called stooge sort, the 3 stooges, plus the fact that it's not a good algorithm. But given an array of length n to sort,
It works.
it works, but it's less efficient than selection sort. Okay? So given an array of size n, it makes 3 recursive calls on arrays of size 2/3 n. Okay? So A is 3. That's obvious enough. It's making 2 recursive calls. But a lot of people want to say B is 2/3. But actually, B is 3 halves. I mean, how do you know B can't possibly be 2/3 if we're talking about divide and conquer algorithm?
Then it'd be getting bigger.
The array will be getting bigger each time, right? You divide by 2/3, you get something bigger. See, B has to be what you divide n by. So in 2n over 3, are we dividing n by 2/3? No, we're multiplying n by 2/3. Just like here, we're dividing by 2, we're multiplying by 1/2. So if I wrote it like this, 1 times n over 2, you wouldn't say B is 1/2, you'd say B is 2. It's the reciprocal of the 1/2. So here, B is not. What do you divide n by to get 2n over 3? You divide by 3 halves. n divided by 3 halves is equal to 2n over 3. So B is the thing in the denominator. So you've got to write it so there's a thing in the denominator, and that's the B. Yeah?
So what happens when B is less than 1? Like, is the problem getting bigger?
Yeah, if B is less than 1, then the problem's getting bigger, and you're not going to use the master theorem there either. Or I mean, if the problem's getting bigger, it's not.
It could hit a big base case.
I guess it could work up toward a base case. We haven't seen any examples like that. Actually, we have. What's the one problem you've looked at where the problem size kept getting bigger and bigger? Do you hit a big base case? Yeah.
Was that the Mertzsort where you merged one array into 2, and then you added another one into the already merged, and then one more? Is that what I'm talking about?
Yeah, in that case, yeah, the answer is getting bigger, but I wasn't thinking about it. There's another better example. Yeah.
Dynamic arrays.
Dynamic arrays? No. I guess you should read my mind. Yeah?
I don't know, I was thinking the water pouring problem.
No, not the water pouring. I'll take one more shot, yeah.
Modular experimentation?
No, not that either. It was the problem where you had an array of unknown size, right? And the first step was to probe it until you found an index that was in the array and one that wasn't. And then you do a binary search in here to find the end of the array. But the recursion, the first step, you would like check at index 1 and then index 2 and then index 4 and index 8. So it was sort of a telescoping search until you reached up. That's sort of the inverse of binary search. Yeah, anyway, that's what I had. Okay, what's D? Yes.
The time complexity of the overhead.
Well, right. O of n to the D is the time complexity of the method overhead. And what do I mean by method overhead? Yes?
Everything else other than the actual recursion that you do.
Right. Everything that's going on except for the actual recursive call, or recursive calls. Yeah?
So that means like, if your algorithm had like a selection sort at the top, that would be overhead, and
Right.
D would be 2 because selection sorts and
Right. So if you before you make the recursive call, you do a selection sort, or after you do the recursive call, you do a selection sort on an array of length n. Then the overhead is at least n squared. Depends what else you're doing. Yeah. It's just you just do plain old complexity analysis, but you ignore the cost of the recursive call. Account for everything else. Yeah.
When the overhead is log n or n log n, do we put a bound on that that's numeric, or do we say some value less than
Well, if
2?
if the overhead is n log n, if that's the overhead, and you want to apply the master theorem, you've got the complexity has to be in the form of a polynomial. So what I do is I say, okay, this is just O of n to the 1 plus epsilon, where epsilon can be any positive real number. And hopefully, it turns out that it's enough to know that it's slightly, something more than 1, because there's another, it turns out the exact value of epsilon doesn't matter, because log base b of a is bigger. Yeah?
When you mentioned recursive multiplication earlier, are you talking about school book multiplication?
Well, no, there was grade school multiplication, which is iterative, and then we talked about recursive multiplication algorithm where we split, it was our precursor to Karasuba. We split the two numbers in half, but we made 4 recursive calls. That was still n squared. But then with Karasuba, we got down to 3 recursive calls and got something better. All right, let's take a quick break and we'll continue with this. Oh, okay, let's get started. So, some of you may be watching these videos to review. If you do, if you notice any audio problems, could you, you can post comments on these videos, I think, right? Post a comment telling us where the audio gap is. We keep getting reports about gaps in the audio, and some of the early ones, the audio is totally screwed up. I'm interested in, you know, in learning there's a 5-minute gap in the audio. I want to find out how frequent this is to see if you've got a real problem or not. So yeah, any feedback you can give, I'd appreciate it. Okay, we're talking about analysis here, recurrence relations in the master theorem. Blended algorithm. So what's the recipe for a blended algorithm? And what's it have to do with divide and conquer? Yeah?
At a certain point where if you continue with the first algorithm, it would be inefficiency, switch over to an algorithm that could finish it out in a more efficient manner.
Okay, so the idea is you have some divide and conquer algorithm that keeps splitting the problem into small pieces, and at some point the problem gets small enough that instead of continuing to split, use a different algorithm to solve the problem for the piece. So why is it necessary? We're talking about blended algorithms. Why are we talking about, why do you have to have a divide and conquer? Yeah?
You must reduce the problems that are small enough that the other algorithm can handle it.
Okay, so you need something that, you know, divide and conquer is splitting the problem up into small instances of the same problem. So you got to have that so that you've got something, when the problem gets small enough, you're still solving the same problem. What's the relationship between the divide and conquer algorithm and the other algorithm need to be? What properties they need to have? Yeah?
The other algorithm is like a higher base case for the recursive.
Okay, so the other algorithm becomes a new base case for the blended algorithm. But what has to be true about the, so typically the divide and conquer algorithm is asymptotically faster than the one you switch over to. So why do you switch over? Yeah?
Well, because that's, I guess, where the running times would kind of be crossing you and backing them. Because the running time with the other algorithm is lower.
Okay, so it has to do with when the problem gets small enough, the asymptotically more complex algorithm turns out to be faster on small problem sizes. So, for example, you might have quicksort, which is asymptotically faster than insertion sort, but for a small enough array, insertion sort's faster. Even in the long run, it's dull. So you switch over to insertion sort at some point. Why would quicksort suddenly become not as good as insertion sort on a small array? Yeah?
Because it uses recursion and that has bigger overhead.
So, yeah, so think about, say you have an array of length 32 and you start doing, and you do quicksort on it. Well, it divides it up into arrays of size 16, and 8, and 4, and 2, and 1. There's a lot of splitting and recurring going on. But there's comparatively less if you're doing an array of size 1 million. You know, the ratio of recursive calls to the size of the array is a lot lower, getting from 1 million down to 32 than it is to get 32 to 1. So the recursion overhead tends to kill you on small arrays. So we switch over. Yeah?
Okay, this is another kind of examples where we're used to asymptotic complexity analysis, so we've ignored all these leading constants and things like that. But now what matters a lot more in this case.
So the lower terms in particular, you know, in the long run they don't matter, but in the short run they do. And it's for small problem sizes where they might really kill you. So that's the deal with blended algorithms. What about tail recursion elimination? What's tail recursion elimination? When can you do tail recursion elimination? Well, what is tail recursion? Yeah.
When you end one of the recursion sets with a recursion call, you can just turn that into a while loop, basically.
Okay. So you know you've got tail recursion. If the last thing you do in the recursive case, or in a recursive case, is make the recursive call. Whatever result you get back, you immediately return as your result. You don't do anything else to it. There's no post-processing after the recursive call. That's called a tail recursion, because the recursion comes at the tail end of the method. And it is possible to mechanically, you don't have to use any smarts or cleverness, so a compiler can do it, turn tail recursion into a loop. It doesn't improve the complexity, the time complexity. What does it improve? Space complexity, because you don't have the stack space that's built in. Okay? Now I know you haven't gotten much or any practice in doing the optimization. I'm happy if you just understand what it means. So you know what it means when someone says tail recursion elimination. Literally eliminate a recursive call in favor of a loop. Yeah?
So is there like a trick where we're just going to assembly and just swap the jump and length, just a jump? Is that what it is?
Yeah, I mean, it can be slightly more involved than that, but basically, instead of make a recursion, you just, there'll be a condition that says, you know, if the problem is bigger than this, make the recursive call. And you just replace that with, while the problem is bigger than this. Now, I don't want to, in the interest of time, rather than try to describe what the optimization looks like I say, I'm just happy if you know what the optimization is. Yeah.
You said there was an iterative solution to Mertzsort, right?
Yeah, but that's not, you don't obtain it via tail recursion.
Yeah. I'm just wondering, like, if we're so concerned about spacing complexity, why don't we just try to turn every recursive method into like an iterative solution? Is it just because it gets hairy and ugly and super unelegant, or?
Yes, and in some cases recursion is required, yeah, there's not always a constant space loop you can use to solve a problem. Some problems are complex enough. Yeah?
My understanding was that you can't technically turn any recursive relations into iterative relationships, but sometimes it can be very difficult to do that.
Well, it can be very difficult. Furthermore, yes, you can replace, ultimately the computer is just a big loop. So you can take a recursive algorithm and turn it into a loop by having your own stack, basically simulating recursion. So that's why I was saying sort of a constant space loop that replaces recursion is not always possible. Okay, and then we explained a lower bound on sorting. We used decision trees to argue that comparison-based sorting has a lower, any algorithm has always have a worst case that's in line. Right? So it's, both the technique that we used is important to know and also the result. Any questions I can answer about that? Yeah?
You said that there are sorting algorithms that are not comparison-based?
Yes, there are sorting algorithms we haven't looked at yet. We will look at radius sort as a non-comparison based sorting algorithm that actually runs in linear time. The problem with non-comparison based ones is they're not general purpose. They typically don't work on all types of data. Data has to have certain properties. But if you're interested in sorting integers, you can just sort them with radius sort. Okay, this is a chapter on depth-first search, graph decomposition. The idea was we did depth-first search not because we wanted to find paths. In fact, when we did depth-first search, we didn't record any paths. We're doing depth-first search just to analyze the graph, typically to either classify the edges or to find pre- and post-times. So you should be familiar with the different types of graphs, like directed versus undirected. We've seen examples of both. Weighted versus unweighted. Talking about the edges here, we've seen that. Sparse versus dense. So what's it mean when I say a graph is sparse? Yeah?
It doesn't have very many edges to other nodes.
It doesn't have very many edges compared to vertices, but actually it's a more technical definition, yeah?
It's not dense.
It's not dense? Well, actually there's space between sparse and dense. So there can be graphs that are neither. Yeah? Well, it's not that E is less than V. That's getting at it, yeah?
E is not V squared?
Well,
or E is not approaching V squared?
We can say it with a positive, yeah?
Is it the minimum number of edges possible?
It's not the minimum number of edges possible, because that would be 0. Yeah?
You just say E cannot be V squared.
No? No, we say E is O of V. Okay? So you can have, E could be 4V or 2V or 1/2 V or 0 or whatever. But it's not, you know, E can't be V log V, for example, which is not V squared. If it's sparse, you've got a linear relationship between the number of vertices and number of edges. And often I'll say assume the graph is sparse so that you can simplify your complexity determinations. I mean, if you come up with a result that says the algorithm is e plus v log v, and I say the graph is sparse, how can you simplify e plus v times log v? Yeah, it just becomes v log v. The e is the same as the v, or smaller, so it goes away. Yes?
So that isn't really a determination you could make just looking at a single graph. That's the determination you would make as to a category of graphs. Because if you just show me a graph, you know.
That is true. An individual graph, I say, is it sparse? It's, you know, it's an asymptotic notion. It depends what happens to that type of graph as the size grows. And then dense means you've got omega of v squared edges.
So what do we do when that's in between?
In between is neither sparse nor dense. So I guess you say it's neither sparse nor dense. Cyclic versus acyclic. So talking about a directed graph, that's an often a thing. Cyclic versus acyclic. We looked at two graph representations, adjacency matrix and adjacency list. So you should be familiar with those. I love to ask questions, you know, how complex is this problem on a list versus a matrix? You had examples like that on the assignments, yeah?
So we will not have to worry about like a list of edges representation?
No.
Okay.
Yeah.
For this measure?
Yeah. Okay? Depth first search, okay? We did that a lot. You need to be able to take a graph and figure out, if we do a depth first search under these constraints, what are the pre and post times? Yes?
When you talk about topological sort, is that just referring to sorting them based on their post?
Well, first of all, right, so topological sort is related to pre and post times. It's, first of all, it only applies to a DAG, so it's really technically wrong to say that you're going to topologically sort a graph that's not a DAG. And yeah, it corresponds to a topological sort of the DAG is an ordering of the vertices by descending post time for some depth first search on the DAG. Pre and post time. So yeah, it's easy to make up exam questions where I say what's the pre and post times of these things. We can use pre and post times to classify edges. And we saw some examples of that where we talked about tree edges and back edges and cross edges and forward edges.
What was pre times used for?
Sort of the relationship between the pre and the post times. You know, if the pre and post pair was nested inside another pre and post pair, that indicated one kind of edge. Off the top of my head, I don't remember what kind. There was a slide somewhere that talks about determining whether you got a forward edge, a back edge, cross edge, depending on how the pre and post times of the two endpoints relate. So that's one use of pre and post times.
Is there such a thing as like in between times, like between? This forms sort of like a tree, right? So these are like pre-order and post-order operations.
I don't know if they're pre-order and post-order. I wouldn't do that. Pre just means what time do you start exploring this vertex, and post is what time are you done exploring the vertex. But it just has all these useful properties. All right, yes?
What's the difference between a tree and a forward edge? Because I know that you use the same pre and post times to find.
Right. A tree edge is one you actually followed during the depth first search. And a forward edge is one you didn't follow, but which goes from an ancestor to a descendant. So it goes forward in the tree. All right, so in 1410, I have the students repeat after me a lot. And what I have them repeat is, the question is, what is this mean in Java? And the answer is, the object on which the method was invoked. And so I'll put on the exam, explain what this is in 8 words or less. Or sometimes I even put 8 boxes. The object on which the method was invoked. And I tell the students, this will be on the final. And they still miss it. Some still miss it. So, what's the first step in most DAG algorithms? Topological sort. That will be on the exam. And I bet you, hopefully none of you, but someone will miss it, right?
I put money on it.
Yeah. Okay, that's just another thing. Linearization is another word. Linearization, topological
So
sort.
in one word.
Could put in one word, that's true. All right, and then the form that algorithms on DAG take is you do a topological sort, so you got the vertices in some order. Sometimes you need to do it in topological order, from high post time to low post time, sometimes reverse. And then what you do is just define an operation that you do on each vertex. And that usually you determine, the algorithm is determining a value for a vertex in the DAG in terms of either the values that have previously been computed for all the vertices to which this vertex has an edge. Or alternately, you may be computing it in terms of all the vertices that have an edge to you. And that determines whether you want to do the topological sort or the reverse topological sort. It doesn't involve recursion. The reason you're doing that, you do the depth first search to do the topological sort. That's the recursion. Now you've got an order. Now you can just write a non-recursive method that you apply in turn to each vertex, and you just fill in the blanks. And by doing the topological sort, you're guaranteed that by the time you need a particular value to be computed for a vertex, it already has been computed. That's the ordering part. Okay? I'll take that form. I imagine there'll be a question on the midterm where I will ask you to, like there was on the example midterm, there's a problem where I define a DAG problem and ask what is the simple computation that you do for each vertex. Right? I'm looking for something non-recursive there. Define the value for the vertex in terms of either all your immediate ancestors or all your immediate descendants. Any other questions about that topic? Okay. And we saw how you can determine the connected components on an undirected graph. How do you do that? Yeah.
Reverse element directions of the...
Well, that's on those are strongly connected components on a directed graph, as you're thinking of there. But what's a connected component on an undirected graph? Yeah?
With that, don't you put like a counter for the connected component before and after the explore? And then
Yeah.
everyone that has the same number is part of that connected
Yeah.
component?
So basically, to find connected components on an undirected graph, you just do depth first search. Each call to explore will visit some vertices. Those are a connected component. And what she was saying is that you could just have a counter, and the first time to explore, you label all the vertices with a 1 that you visit. The next call to explore, you label them with 2s and so forth. So you're numbering the vertices according to their connected components. That's a lot easier to think about than strongly connected components on directed graphs, which is a little slippier concept. But that's the algorithm where you reverse the graph and do a depth first search and use the post times to control the subsequent depth first search on the original graph. Yeah.
So, correct me if I'm wrong, so if they're connected components on the undirected graph, does that also mean makes a cycle? Or is it?
Well, it's undirected, everything's a cycle. It goes both ways.
Yeah, the notion is simpler on an undirected graph because the edges are two ways. So if there's an edge between two, if there's a path between two vertices in a directed graph, they're in the same component. So you only have multiple components if the graph is disconnected in some way.
And we do that at the DFS level, not the explore level, where we number them or tag them.
Yeah, they're numbered in the they're numbered. All the vertices that are discovered in one call to explore from depth first search get the same number. Okay, about graph search. I'm running out of time here, but this is where we talk about breadth first search. So there's that breadth first search algorithm. There you're interested not in pre and post times, you're actually interested in paths. Then, if you put weights on the vertices, you've suddenly got a shortest path problem. We looked at 3 algorithms. Bellman-Ford, which is really brute force. The shortest path problem on DAGs, which is you can do very efficiently by topologically sorting and applying a simple operation to each vertex. And then Dijkstra's algorithm, which works as long as they're negative, works efficiently as long as there are no negative edges. they all use the same update operation, which basically says, okay, I know how far it is to this vertex. You're looking at an edge from here to here, and you say, okay, I know the shortest path to this thing right now. Is it shorter to go through this thing? And if it is shorter to get here via this edge, you do an update operation. So they just differ in how they decide what update operations to do. We looked at a couple examples of priority queues. And I know that those of you that worked on the CAS problem and some of you implemented your own priority queues, you looked at your own too. A little hard to get exactly right. And the final topic, in the last 30 seconds here, is modular arithmetic. So if I give you an equation like 5 plus 6 equals x mod 8, you should be able to say that's 3. Right? 5 plus 6 is 11, mod 8 is 3. Or if I say, solve for x, 5x equals 1, mod 11.
Congruent.
Yeah, when I say equal, I mean congruent. So solve for x, you should be able to solve for x in simple modular arithmetic equations where the numbers are all really small. Okay? Well, that turned into a good review. Sorry we're a bit rushed at the end. If you need more, Stefan's got you covered.